So any questions about the general idea of this? Pretty much it'll be similar to the quiz, except of course longer, where you get the test on through Blackboard, and there's some problems when I gave a test yesterday, as you sort of knew with all the beeps. So it'll be available about 10:20, and you have to submit it through Blackboard by around 11:45. As long as you're fairly close, I'll assume it's okay, because of course it could be just that it took a little while to upload. So 11:45 with a little leeway. If you do have any problems, send me an email, either getting the test, which obviously you should email as quickly as possible, or if you have trouble uploading, so if you can't upload to Blackboard for whatever reason, just send it to me as an attachment and as an email. So any questions about the test in general? Okay, so as I said, let me look at ones that we haven't on a quiz, which is 4.2, 4.3, and 4.4. So on the review, those are problems 9, 10, 11. So let me do a variation of 9. So let's have a vector field being, make it nice and simple. Since I'm making them up. So we have a nice, fairly simple vector field. And a really simple C. In this case, just the line from, or the line segment from 1, 1, 1 to 2, 3, 4. And I want you to find the line integral. So this is the 4.2 version, where you can't use the two different ways from the next two sections. So here, this is not conservative, because the derivative of q with respect to x is y, derivative of p with respect to y is 0, so they're not equal. So even just looking at that, you can see it's not conservative, so we can't just get the potential function and plug in the endpoints. Obviously, this isn't closed, and you don't want to try to close it because you'd make it more complicated. And for this type, either it would be a line or a circle, because I assume those are the two that I assume you know how to parameterize, or I could give you the parameterization like I did on the review. So here, what is the parameterization? And for this, if you're parameterizing, there's usually more than one way to do it. But for lines, the basic thing is basically what we did in chapter 1. So the vector is just the end point minus the starting point, so 1, 2, 3. And then the line is the point we start with plus t times the vector. And if you do it that way, then it's simple in terms of c. It's just going from 0 to 1. And you can pretty easily check. If I put in 0, I get 0, the starting point 1, 1, 1. If I put in 1, I get the 2, 3, 4. So I'm going from one point to the other. Or we really want it in this form. It is 1 plus t, 1 plus 2t, 1 plus 3t. And now what are the two things I do to get the line integral? I do f at, so plug in the parameterization into f. So it's equal to x, the 1 plus t, xy, and z. And then take the derivative of the parameterization. Right. And then we do the integral from 0 to 1. And what do I do with the two vectors I've got? Just take product. So it's going to be, which I'm not going to do, but since I made it up. So I'd get the 1 plus t plus 2 times the middle term plus 3 times the 1 plus 3t, which is a quadratic. It's not difficult to do, but I'm going to be lazy unless you really want to see it. So this is the 4.2 type problem. And as I said, either you're going to parameterize a line or a circle, or like the review, I'll give you the parameterization. So any questions on this? Okay, so I'll only do one from 4.3, which is a one like 10, and again, the variation. Okay, so here is a vector field. And I ask, is it conservative? And again, there are the two ways of doing it. One is just look at all the second mixed partials. Or the other is to look at the curl. And let's see if I messed this up. So derivative of r with respect to y is 3x. Derivative of q with respect to z is 3x. Derivative of p with respect to z is 3y. Derivative of r with respect to x is 3y. Everything's 3y. Derivative of q with respect to x is 3z. And derivative of p with respect to y is 3z. There. It is conservative. And now we want to find the potential function. So how do I find the potential function? So for example, I can integrate what with respect to what? And I might as well start with the first one. So I can integrate p with respect to what? Yep. So I get the 3xyz plus x squared. And since it's just with respect to x, I might be missing y's and z's. And then q with y with respect to y, r with respect to z. And so I get, again, the 3xyz, and that's it. Again, I might be missing x's and z's. Some ways, if you want to be lazy, you can skip things that you've already done. So I don't really need that first term every single time. Now our plus c is our usual plus c. So kind of the setup. And remember, for two-dimensional one, if there are only two variables, we just have that last one. We just need q of x to be equal to p of y. So now the part C will be, now let's find the integral over C for a given value, given curve C. So any questions on the setup here? And you might, since I just made it up, you might have to remind me what the function is in the next slide. But any questions? So C. Okay, so let's find the integral of the potential, the vector field that we had in the last one, if we're going along this path. And since we found it's conservative, what do I just have to do? Actually, as you're going to answer me, let me start. Right, just the integral with the endpoints. And is that what we found the potential function is? Okay, so now we just care about plugging in the endpoints. So kind of a boring example here. So if I put in 0, 4, 0, I get 0 plus 0 plus 0. And if I put in 1, 0, 1, I get 0 plus 1 plus 4. So I get minus 5. As always, you're double checking my arithmetic. But so remember, the idea is if something is conservative, then you take the equivalent of the antiderivative, which is find the potential function, and then just have to plug in the endpoints. Also, if I was doing the same thing, and I, again, had many steps, I went from 101 to 232, from 232 to 400, from 400 to 040, and then from 040 to 101, what would be the integral? And notice, I don't actually need the potential function. So if you have a closed curve as your C, you should definitely check to see if it's conservative, because it's usually, especially if it's two variables, pretty quick to check. And then it's just a really easy question. So for a closed curve like this one, definitely check to see if it's conservative. So any questions on this? Okay, so then one similar to the last one, number 11. So given the vector field x squared plus 5y, 3x plus e to the y, find, again, this is 4.4. So these three problems, the first one was 4.2, second one was 4.3, this is 4.4. So this one, you can see it's a closed curve. So going from what we did in the last one, we should be checking to see if this is conservative. Is this conservative? And so remember, last one, we just did that last piece, which is if this is P and this is Q, we need P of Y to be equal to Q of X. But the derivative of P with respect to Y is 5, derivative of Q with respect to X is 3, so therefore it's not. So it's not conservative, and as I said, you should definitely check, especially because, so this is going to be Green's theorem. For Green's theorem, it's always going to be two-dimensional, so it's a pretty easy check. So Green's theorem says if we have a closed curve, then the line integral of the path is equal to the double integral over the region of q of x minus p of y. And in some ways, this is kind of a typical type thing that sometimes will come up on tests and finals if we want to put in a fairly quick problem, at least hopefully quick for most of you, which is in this case, q of x is equal to 3, p of y is 5, and so that's a constant. So do I actually have to do the integral here? Do I have to set up the integral and go through the antiderivatives? Nope, because since it's a constant, I can pull that out, and the double integral is just going to give us the area, right? And the area of this is 1/2. And therefore it's -1. On the one in the actual review, you'll notice it doesn't always make it so you don't have to do the integrals. The one on the review, we got back something where you actually had to still do the integral. But if I want to throw in a quick problem, then I can do this. And notice, I can then make these, the rest of the part that's going to go away, relatively complicated, which is encouraging you not to do it using the methods from 4.2 because then it'll become messy. Also, remember, if you have a fairly long one and so for example, C was just from the origin to 1, 1 to 0, 1, if the piece that's missing is fairly simple, it will sometimes make sense to close it so you can use Green's theorem. So instead of having to add up the pieces, so for example, if I had, let's make it a complicated thing. If I did something like that, and I stopped there, then using the 4.2 method would mean I'd have to do the 4 pieces, do each of them separately and add them all up. Whereas this is not a good example. Well, actually, it's not bad. I could add in an extra piece, close it, which means I could then use Green's theorem, and then subtract off on that one little piece. So if it's not closed but close to being closed, it might make sense to use Green's theorem, and you might want to check what is q of x minus p of y, because if that's simple, then it will make sense. So any questions on this? So this is nothing. Okay, so those are the ones that we haven't had on a quiz. The other stuff we have. So from here on, now it's what you have questions on, and either a question on an actual problem or a variation. Some of them, at least, I can make up pretty easily. You should notice that if you look at the answers, there were a couple typos in the actual questions. So in one of them, I forgot to give you a radius, and in another one, I did something like y is equal to x squared plus y squared or something like that. But I have the corrections in the answers. So I said, from now, kind of like the test 1 review, I'll stay as long as you have questions. So any ones that you want to look at? So either general questions or specific questions about one of the problems on the review, or you want to look at a question similar to one of the reviews. So let me know. In some ways, as you're maybe thinking, I don't have necessarily office hours tomorrow, but it's pretty easy to make sessions Zoom is usually a little bit easier. So if you have questions, send me an email and I'll set up a Zoom session so I can answer your questions. So I don't officially have office hours tomorrow, but I can easily make it because, of course, I'm home. So just email me. So yes, any ones that you want to look at. 6 or 7. Okay, so 6 and 7 are cylindrical and spherical. And in some ways, there aren't too many versions I can do. But let's do and there just aren't too many I can do, but so here's one. So here I want to integrate something. Since I'm not going to have you do the integral, it doesn't really matter what that is, although we might have to change it. Over the region above the xy plane, so we're top half, bounded by the sphere of radius 5 and the cylinder of radius 4. So if I was looking at this from the front, because I can't draw the three-dimensional thing, in the front it would look something like that. So first little thing is, for this, what type of coordinate system do we want to use? Do we want to use rectangular, cylindrical, or spherical? Yeah, cylindrical. So in some ways, either cylindrical or spherical. You can see it's not going to be completely great for cylindrical because we do have the sphere. So we're going to get a square root of something squared. On the other hand, it's not going to be great for cylindrical either, because if I draw a typical radius, you can see, oh, it's hitting, at some points it's hitting a straight line, which is bad. And at other points it's going all the way to the edge of the sphere. So we'd have to break it up into pieces by seeing where the two intersect as an angle. And then we'll have to get essentially this line, x squared plus y squared is equal to 16, into spherical coordinates, and that's not going to be nice. So in some ways, neither one is perfect, but let's try cylindrical. And let's look at the projection. So projection is just going to be a circle. And a circle of what radius? Because in some ways we have two possible ones. So is it going to be the x squared plus y squared is equal to 16 or 25? Yeah, so 4. So radius 4. So this will be our r for the second part. So the first one, we need what's the lower limit, which is the xy plane. So that is 0. This is where the cylindrical isn't going to be real nice, z will be equal to solve for z. You can, of course, do this in one step if you want. So when I bring it down, if I'm doing it the dz, dr, d theta, I'll only do it in the steps here. So xy will become r cosine theta, r sine theta. Because we're in polar coordinates, we're also going to get the extra r as usual. And what do the limits become? On the inside one, that's still 0. The upper limit becomes the square. It's hard to write the square root. The square root of what? Yep. R goes from so what are the limits for the middle integral? Here to 4. And finally, for the outer integral, they are 0 to 2 pi. The other variations where cylindrical are going to come up are either paraboloids, because the projection of that is going to be a circle, or a cone, because the projection of that is also a circle. So those are kind of this along with those two are kind of the 3 main types that might come up. And I think in this one I had 2 paraboloids hitting. So to figure out what the projection is, remember you're looking at the biggest point. So any questions on this? For the spherical, there just aren't too many examples because what we would like is that is to make it nice, we need kind of a slice of the sphere. And so, for example, we could do a quarter sphere, or about the nice example is we're looking at where a cone intersects a sphere. So I did the cone intersects a sphere, about the only other type. So first, any questions on this? About the only other type. Would be something like this. So we're looking at just part of a sphere. So in this case, the setup is pretty easy, though I'll write down some of the details below it. So since it's a sphere, and if I'm doing it, give myself space to put stuff in the middle. What are the, oh, oops, I'm missing something. A solid sphere. Let's say I have radius 5. Then what would be the limits for a row? 0 to 5. The limits for phi would be 0 to what? And I'll ask, you'll remind me what would be if we did the whole sphere. Because that would be pi over 2, and theta would go from again 0 to pi over 2. So remember, for the theta, the full circle, the full sphere is from 0 to 2 pi. The two things about phi you have to remember is we're looking at it from both sides as we rotate it around. So the full sphere is 0 to pi. And also we're measuring from the positive at z-axis down. Now we have the conversions. What does (3x squared plus 3y squared) become? And then we just have to write that in terms of rhos and phis is equal to which. Okay, I was going to say it's kind of a pain. Right, r is equal to rho sine phi, so we get that. I lost the squared there. And then yeah, so I I noticed about this same time you did it. And then we get our always add in, which is rho times r. So we get a third r as always. So this would be a limit. As a quick add-on question, here I'm looking at just in the first octant. What if I wanted to look at the top of the sphere? So obviously that wouldn't change the function. What would, so for top half, right, so this wouldn't change, this wouldn't change, but this would become 0 to 2 pi. And as I said, this is kind of the typical sphere type things, which is either it's part of a sphere, the first octant or the top half or something like that, or it's cones, because those are easy to, because cones, remember, spherical coordinates are just angles. So any questions on this? Okay. Any other ones that you want to look at? So because we are having these delays, I'm going to stop recording. So in some sense, if you think you're ready, we're done. Remember the few things. One is I don't officially have office hours tomorrow, but if you email me, we can set up a session on Zoom. So let me know if you have questions. Second, I will email Nicole and Carson and Alicia because they are taking a different time. If you're anyone besides those three and you need to do it at a different time or something like that, then you will email me, including you have another test on Monday or whatever. So if you're not one of the three I mentioned, send me an email and we can set up a different time. So I'm going to stop recording, but